Here it says, assume that a log rotor starting current of 90 amps at a lagging load factor of 0.3 is supplied to a motor which is operated discontinuously. A normal operating current of 15 amps at a lagging power factor of 0.8 is drawn by the motor from the 2.4 4.1 kV feeder of problem 2. And the feeder in problem 2 had that impedance, right? Assume that a series capacitor is desired to be installed in the feeder to improve the voltage regulation and limit lamp flicker from the intermittent motor starting, and determine the following. Now, this was a solution that was used for a flicker problem because there was a sawmill. A chipper mill, sorry. There was a chipper mill. A chipper mill, basically you get a tree and you get a lot of blades that are producing chips. And then the chips then go into a paper mill, my guess, to produce paper. And this is in southern Arkansas. And the chipper mill was 13 miles, 13 miles from the substation. And so every time that log, and what's happening? When the blade hits the log, what's happening? For a very short period of time, obviously the rotor stops. Then eventually, you know, the wood gives out and the rotor keeps turning. But every time that, you know, that blade was hitting the log, there was a lot of flicker. And so if you were in a house next door, right, to the chipper mill, right, if you were working for the chipper mill, they were providing you a job so you wouldn't complain, right? But if you are a neighbor right next door to the chipper mill, you see the lights going up and down, and it's annoying. So that's they were complaining. So to limit lamp flicker, right? And so they install a series capacitor. But the problem was that the solution was not very effective because the feeder was too long. And so the amount of capacitors that they put was not sufficient. They spent like $250,000 to put these capacitors, right? So it wasn't something. And so the voltage dip due to the motor start before the installation of the series capacitor, and the necessary size of the capacitor to restrict the voltage dip at motor start to no more than 3%. Right. So what's the problem with this? Well, the problem is that you get 3%, but as soon as the motor starts, you go back to normal conditions. Right. And then you start the motor again because whatever is the case here, right, it's operating discontinuously. In the case of the chipper mill, every time that the blade was hit, right, there was. And so the question is, the dip is 5.3%, and what they want is 3%, so you need to calculate what is the capacitors. So the capacitor is connected in Y, and basically what you do is, well, you want this to be 3%, 2.4, right, is the rated voltage, right? You are calculating the dip as a percentage of the rated voltage. So you solve for VD is 72 volts, right? Now this problem can be posed, and instead of using a series capacitor, could be posed as, what about if you use a shunt capacitor? Right? And in fact, that's how it's being solved, right, in this particular case, right? It's being solved considering a shunt capacitor, right? And so in order to reduce this to 3%, what do you have to do? You have to reduce the current. So the problem in the textbook has been posed as using a series capacitor. It's not a good solution in distribution systems. So that's the reason why Dr. Balda work the problem considering a shunt capacitor, right? And so here you have the system, this is your feeder, here is your motor, this is the current that is drawing, right? And this is basically the capacitor current. So you know that that is 72, right? And so that voltage drop of 72 that you got it from here to be 3%, right, is equal to what? Impedance times current, right? This is impedance times the current, just the magnitude. So I calculate here that what I want is 50 amps on the source. Well, I know that the magnitude, right, so what you got on the top, right, is KCL, right? The sum of the current at the nodes is equal to 0. And what I do, I have here a figure, right? If I have a circuit, I can use KVL, I can use KCL, and analyze it. So this is my node. So here I have the source current, here I have the load current, and here I have the capacitor current. Now, the capacitor is in parallel with the load voltage. Do I know the angle for the capacitor? Right? It's 90 degrees, right? It's an ideal capacitor, right? Do I know the angle for the current? Yes, it's given, right? Now, what I do not know, what is the current, the magnitude, and the angle for the source. But what I do know is that the voltage drop here is 3%. And I can use that knowledge to solve for the magnitude of the current. So then I have here an equation, right, that tells me what is the only unknown that I have there is beta, right? And the other unknown is the amount of capacitors, right? So the question is, what is the amount of capacitors that I need to install in the system so I can get a 3% voltage drop on the feeder? So there are two unknowns on that equation. IC, the magnitude of the capacitor current, and beta, the power factor of the source. Well, so basically there I have, once again, what you have there, real and imaginary. There are two equations. Have you used this before? Yes, chapter 3 all over. Is the same equation? No, but it's the same concept, right? You got a complex equation with two unknowns. What is 50 times cos of beta equal to 0 plus 90 cos of minus 72.54? That's the real part, right? And so, and I have a mistake here, I just noticed. Here it has to be sine, right? It has to be sine of cos of beta, right? This is the real part. This is the imaginary part. This is 1, so I calculate that the current on the capacitor is 127.93. I know that that's 90 degrees, so I can calculate now what is the reactive power on the capacitor. If I'm using this equation that I have there, what I'm calculating? The three-phase power, the single-phase power, or what? What is 2,400 volts? Per phase voltage, line to neutral. What is IC? The current through the capacitor. What I'm assuming that capacitor connection is? Is Y connection, right? Line to neutral, right? All start here, right? What is this? This is the per phase. This is the line, this is the neutral. That's how you solve three-phase systems, right? If you learn something in this class, that should have been something, right? So basically what you got is 30.7 kVAr per phase, right? And here said 307, I picked up 350, which is the largest nearest value. This is different to what we did up to this point, right? Up to this point, right, we use the smallest nearest value. So why are we changing? See, that's the reason why memorization doesn't help. So why are we using the largest nearest value? Why we are not using the smallest nearest value? No.
Because we went 3%, we can increase it, we got a bigger one.
A smaller one. If you have a smaller one, you wouldn't get 3%, right? You would get a voltage drop which is higher than 3%. So you go for the nearest, largest, because you want to guarantee that you are going to get less than 3% because you want to solve a lamp flicker problem. Right? Why were we choosing the smallest capacitor bank? When we were taking into account what? Over voltage, overcompensation, right? So the criteria change, right? Here we are not, do we have an overcompensation problem? Look at the power factor. This should be, right, 50. I think it should be negative, but because if you don't have capacitor, what is the value of beta? Minus 72.54, right? If there is no capacitor, the source current is the same as the load, right? So beta should be, I need to verify that. So that's basically what you have. You see, the criteria is different now. Now you are using the capacitors to achieve a voltage drop which is under 3%, and what do you hope? That your flicker effect goes away, that is not noticeable. The problem in the textbook that uses a series capacitor, what does it happen? It reduces the 1.35 So that's what we have. And so here we choose that. The largest because, remember, we want to guarantee that we get under 3%. And so here we have the equations to calculate, right, the capacitance. And so here refers to page 386, which I think are the ones that I told you you shouldn't consider those. Well, no, sorry. Right, these are the equations, right, that we already went through here, right, for that. Right, that's your example 8.2, right.